This is Mrs. O'Neill for AP Chemistry, Chapter 4, Section 3, Acids, Bases, and Neutralization Reactions. Your objective in this section is to explore reactions in which protons, in other words, H+ ions, are transferred from one reactant to another. So let's look at water, for example. Water is really written as HOH. Most professors like to write it that way because the HOH splits into the H+ acid component and the OH- base component. And this is why water is neutral, because it has an acid component and a base component. So pause the video, fill in the blanks, and then play to hear my words. So an acid is something that ionizes in an aqueous solution to form these H+ ions. This H+ ion is really a proton, and you're going to see in the next slide. However, you're going to see this H+ ion is also written as H3O+, called the hydronium ion. You'll see that a little bit more often later on, but I wanted to bring it to your attention now because I do kind of put it in here and there as well. So this is actually called a proton donor. This H+ ion is a proton donor. It's going to give away a proton. It's going to give away an H+ to something else. So let's look at hydrogen as an atom, right? Hydrogen as an atom has one proton in the nucleus and one electron in its outer shell or outer energy level. And when it becomes an ion, the energy level goes away, and what's left over is that proton. So this is why the H+ ion is called a proton donor, because that's all it is a proton. There's no electrons. So there are three types of acids: the monoprotic, the diprotic, the triprotic. Mono 1, di 2, tri 3. So let's look at an example. What is that really talking about? It's really talking about how many H+, how many hydrogens are in that acid. So if there's one hydrogen in an acid, it can only donate one H+ ion. If there are two H+ ions in the compound, that means it can donate both of those. So if we look at an example, we have something like H3PO4, phosphoric acid. It can donate 3 H+ or 3 protons, but it does it in 3 steps. Just so you're aware, like a reaction mechanism, it doesn't happen all at once. So the first reaction takes place and one hydrogen is donated or given off. Then we have that H2PO4 is going to give off another H+ ion, and then finally that HPO4 -2 polyatomic ion is going to give its last hydrogen plus away and leave us with the actual phosphate ion. So you really don't go from H3PO4 to 3 H+ and then one PO4 in one fell swoop. It actually happens in 3 steps. I also want you to take notice about the arrows. This is telling me that this is a strong reaction. It breaks apart in these 2 ions. However, these 2 acids, these 2 polyatomic ions, are really weak because they have that equilibrium yield sign. So this would be considered a triprotic acid because it gives away 3 H+ ions. So here's another example real quick. You have your sulfate. Again, strong acid right there. However, it becomes weak when it becomes the HSO4 polyatomic ion. So I just wanted to bring that to your attention. So you need to remember this, and we've talked about this before. The carbonic acid decomposes very, very quickly into carbon dioxide and water. And some places or sometimes professor, again, likes to write it like this because usually it's in water. But the main one to memorize is that H2CO3 really does not exist. This carbonic acid really doesn't exist because it decomposes so quickly into that carbon dioxide and water. So now how about bases? Well, bases are going to accept those H+ or accept those proton little guys that are running around, okay? Also, you can also think of a base as an OH ion is dissolved in water. So let's look at ammonia. Ammonia is a base, but it doesn't contain that OH-. This is why we say it accepts an H+. It doesn't always necessarily have to have an OH- minus ion in the formula in order for it to be a base. So here we have the ammonia. It's reacting with water, and we'll see that more often later. So it's actually going to accept that H plus from the water, becoming this NH4 plus polyatomic ion and these OH minus ions in solution. So again, that's what's making it a base. So strong versus weak, aha, we remember strong completely ionizes, weak partially ionizes. So you have strong and weak acids and bases. There's that list again. So memorize this list. Anything on this list is strong, totally dissociates 100% into ions. Every other acid or base is weak. So we want to remember that strong are usually ionic compounds. They're the acids and bases on the list. And any compound starting with NH4, and you will see a yield arrow. However, your weak stuff are acids and bases not on the list. Remember solids, liquids, gases, and any equilibrium arrow. And of course, your non-electrolyte would be those covalent compounds. So we want to remember reactants as a solid or a weak substance will break apart to make products, but they stay together in the equations, as well as your products. If your products are a solid, liquid, or a gas, again, they will stay together in all equations. So see if you can come up with an answer and then play the video to get the answer. Hopefully that makes sense. If not, just reread it and hopefully you're understanding that, the soluble versus insoluble. So what is a neutralization reaction? Well, it's an acid and a base reacting with each other and always forming salt, which is an ionic compound, and water. So here we have an acid because of the H+, we have a base because of the OH-, we have a salt because it's an ionic compound, metal with a non-metal, or metal with a polyatomic ion, make an ionic compound, and you got your water there. So a neutralization reaction is just an acid-base reaction, as long as there's enough acid and base going on there, one neutralizing the other. So let's look at a strong acid reaction example. Here we have a strong hydrochloric acid plus NaOH. Again, it's really just a double displacement reaction. Do your outers and inners. And so we're breaking apart your strong outers and your strong inners, right? So you have your outers and inners. You've made your salt and your water. Now remember that that salt is going to be soluble in water. So you have Na plus and Cl minus ions. Ooh, so if that happens, your Na plus are spectator ions, your Cl minus are spectator ions, and your water, which is liquid, has to stay together as a liquid. So your net ionic equation is your H plus, your OH minus, yielding that water. So how about, however, if we have a weak acid with a strong base? It does not completely dissociate, but we want to remember it's still a double replacement reaction or double displacement reaction. So you're still going to do your outers, you're still going to do your inners. However, your weak acid stays a compound all the way through. So here's our complete ionic equation where we have the weak staying weak, the lithium hydroxide breaking apart, and of course our lithium acetate is going to break apart because that's our salt, and our water stays as is. So then what's our net equation going to look like? Well, again, our weak acid stays weak. Our hydroxide acid comes down because our lithium, our spectator ions, our acetate ion comes down, and of course our water stays as is. So just as a reminder, your strong will all break apart and you're forming water no matter what, but your weak stays that weak compound all the way through, even though it's aqueous. So why does this happen? It happens because this OH is so strong that it will grab those H plus ions from that weak a weak acid because it's a source of protons. So this guy is so strong, it's going to grab it, it's going to want it, and it's going to take it. And that's why then it makes that salt, which again ionizes in solution and then makes that water. So we're going to see later on that this is going to be really important titration. In titration reaction, at some point, there's going to be so much OH positive ions taking away all of the H plus ions and forming that water and pushing the reaction over the edge. So the general principle is hydroxide ions are so strong, okay, that we're going to assume it's going to completely react with any weak acid around. So again, just like anything else in the world, anything strong is going to overpower anything weak. So let's do some practice problems. So there's two of them here. I believe one is going to be strong, strong, and one's going to be weak, strong, so we can tell the difference. So we obviously have to decide, first of all, if our substance reactants are strong or weak. That's going to play a big part in the overall reactions. Do our outers and inners. We're going to balance. We're going to look for precipitate. We're going to do the complete ionic. We're going to cross out those spectator ions, and then finish up with the net ionic equation, which is the important reaction. So let's look at number one. Again, you might want to pause along the way, but your molecular reaction should be this guy. So you should have done your outers and inners. You should have done your balancing. And even though this is not a precipitate, your water is kind of like your precipitate because that's liquid. What would be the complete ionic? Aha, since HClO3 is a strong acid, it's going to break apart into ions. So the only thing that stays together from the beginning there is that liquid water. So what would be the net ionic? Crossing everything out, we get 2H plus 2OH minus yields 2 waters. And of course you can reduce if you want to. But at this point, just make sure that you do have everything balanced so things cancel out the way they're supposed to. So if you have a strong acid, and you have a strong base, no matter what, the net ionic equation is water. I will tell you that right now. It's one of the easiest things to kind of pinpoint on your quizzes and tests. If you have a strong acid and you have a strong base, your net ionic equation will always be water. However, for number two, your molecular equation is right there. This guy kind of looks funny. Okay, it looks funny because the way it is, but really what's happening is you're still doing your outers and inners, and your H and your K are kind of swatching away. So if you put the K at the end, that's okay too. Again, that's probably how it's more or less structured anyways. But this time now, we have something that's weak. So our weak acid, okay, our acetic acid, our weak acid is going to stay as a whole. So it does break apart outers and inners for our molecular, but we have to keep it as a whole compound all the way through because it is weak, as well as, again, the water. So notice I even have the equilibrium sign there because it is weak. So what would the net ionic equation be? It's a little different here, isn't it? We even have some ions and some compounds now in our net ionic. It's not as simple as A plus B yields CD, right? It is something like an ion plus a compound yields a compound and an ion. It's not always going to be like what you've seen in the past. Okay, I'll see you in class and do some more practice problems.